Alright, so tutorial number 2. This is going to start off by expanding a bit on the last question we ended off with tutorial 1. Which is just find the solution by elimination of the linear system. We have 3 different equations. So in this case, usually what you want to do is you want to take the first equation, add it to the second, and then take the first one again, and then add it to the third. That's going to give you 2 different equations. Sometimes they won't cancel out such that you will only get one variable, sometimes you will. That's just generally how you want to approach it, right? You want to try to create as many as you can to work with. You won't necessarily add, like you might subtract some multiple as well. If you can see that you are able to do that, I would recommend doing that. In this case, we do see a very nice addition. Right, we have 2x, negative 2x, that's going to cancel if we add. Then we have negative z and positive z. Well, that's also going to cancel. So that's really nice. That's just going to give us y. So we get y equals 3. Noticing the first and the third, when we add those together, well, what are we going to get? Well, once again, negative z and z, that's going to cancel. So we're going to get an x and a y, which is perfect, right? Because we have y equals 3, we get an x and y. Well, we can just sub y equals 3 into this. Get 6x plus 4 times 3 equals 0. Move that over, negative 12. And 6x equals negative 12 goes to x equals negative 2, just divide by 6. So now we have an x and a y. All we need to do is just sub in our x and y into one of these 3 equations. I chose the last one because it has the least multiples, right? So we have 4x plus y plus z equals negative 1. Well, sub our x and y in, and then solve for z. Right, so we get this. You don't have to write your therefore statement like this. You can split it up. So you can say like x equals negative 2, comma, y equals 3, comma, z equals 4. I do this notation because this is something you will learn later on, but you know it's not necessary. So let me find question number 2. Yeah, so this is the one I was talking about where it doesn't exactly nicely cancel out anything, right? You can only cancel out one thing at a time. Very, very important that I mention this. In the case where you can only cancel out one variable at a time, and you have 3 different equations, very important that you cancel out such that you end up with xy and xy again. Or variable 1, variable 2, variable 1, variable 2, because you'll be able to work with your cancellations. So in this case, we're just going to start by adding because the first and the second, because we see that that'll cancel out the z. So we get an xy. So because we got an x and y from our first, we want to add them, the first and the third, such that we're going to get an x and y again, because then we're going to be able to work with our x and y's such to cancel them out. Okay. So first and third here, well, we're going to need to cancel some things out. We're going to specifically want to get rid of the z. So what do we need? Well, we have 2z on the bottom, so we need 2z on the top. Multiply that system up by 2. Subtract them, and we get x minus y equals negative 1. So beautiful, we have 3x minus y equals 1, and x minus y equals negative 1. So once again here, right, you can just subtract them. We see negative y, we subtract negative y from negative y. Well, that's just going to go negative y plus y is 0. So we get 2x equals 2, x equals 1. Now, since we have x equals 1, we can actually use one of these 2 cancellation formulas, right? And sub x equals 1 in to solve for y, right? So in this case, what are we going to end up with? Well, I chose this one, and I'll show that it'll work for either. See, we have x minus y equals 1. Well, sub 1 in here. Subtract it. We get negative 2. Then we get 2. 3 times 1, that's 3. Right? Then just subtract that there. Then what is that going to get us? Well, 1 minus 3, that's negative 2. And that's going to go to 2 as well. See, so it works for either one. So you can choose any. I chose this one. Just less to work with. We see that we get 2. Now, once again, you can sub this into any one that you want. Our x and our y's. I chose to do the first one because it's the least amount of multiples to work with. So x plus y plus z equals 0. Well, 1 plus 2 plus z equals 0. That's z equals negative 3. And I decided to write my therefore like this again. You do not have to, but yes. Yeah, so this one's kind of fun. Find the region that gives the solutions of the linear inequality 5x minus 2y greater than or equal to 10. Show all of your work. So what it's really just asking for is we can suppose that this is like a linear line. I mean, it literally is, but you know. So you're going to want to treat it in that sense. So move everything over and just look at y itself. That's going to give you a lot of information. Right, so you have this, just get y on one side. Treat it like a line. So doing that, we see that y is less than or equal to 5 over 2x minus 5. So really what we're saying is we're saying that this y value is going to be less than the line. Right, so this is going to create this line here. So if we were to graph the line, everything below that line or equal to it is going to satisfy this condition, 5x minus 2y greater than or equal to 10, because we derived it from this. Again, since we have negative 2y greater than or equal to 10 minus 5x, if we get rid of the negative on that side, we're going to have to flip the inequality. Remember that. So yeah, so how can we solve, like if we wanted to graph this out, how can we, do that? Well, we can just suppose that this is an equation, y equals 5 over 2x minus 5. Typically, when we're graphing a line, we're going to look at the x-intercept and the y-intercept, and then we're just going to basically just draw a line through them according to the slope. So, yeah. So x equals 0, that gives us y equals negative 5. Right? That gives us our b for our y equals mx plus b. And then y equals 0, we get this here. Just solve for x, we get 2. So then we can graph out, we have 2, 0 for x-intercept and 0, negative 5 for y-intercept. So we draw a line according to that and the slope. And since it's the final piece that we manipulated was y is less than or equal to 5 over 2x minus 5, where this is the line, everything below or equal to that point is going to satisfy this linear inequality. So 4. Solve graphically the linear system of linear inequalities given by 2 different lines this time. So it's going to be very, very similar. The only thing we're going to do is we're going to consider their basically their intersection points, or where it's satisfied by both. So as I said, it's very similar. So what you want to do is get y alone. For the green one, we get y is greater than or equal to 2x minus 4. Once again, sub your x equals 0, your y equals 0 in there. Find the x-intercept, the y-intercept. Once you get that, you're going to be able to graph it according to the slope. Right, so I did that for green. Same thing for purple. Get the y on one side. Y is greater than negative 2x plus 2. Suppose that is an equation that is equal to. Get x equals 0, y equals 0, y equals 2, and x equals 1. So then we can graph this out. And you'll notice something very important is we have 2 different inequalities that we manipulated. We get y is greater than negative 2x plus 2. That means it's above this line. Right? It's above it. And y is greater than or equal to 2x minus 4. And so what that means is it's going to be greater than or equal to this line. Right? So it's a very neat case where if you imagine this on the left side, none of these red lines are going to be equal to, according to this, all the way up to the intersection point, right? It cannot equal the intersection point on the left, so it's not going to be inclusive. Right, so everything to the left of this intersection point, which I think is, let me just do this in my head. This would be 1.5. I think 1.5, negative 1. So everything to the left, like this, above that line is not inclusive, but everything to the right is inclusive, because we have the green line can be greater than or equal to 2x minus 4. Equal to being right on the line itself. And we see that it is indeed greater than both, right? So yeah, that one's a bit fun, but... 5. Evaluate the following functions at the given numbers. A. F at x equals negative x squared minus 3x at x equals 0 and x equals 5. And g of t. So this is really just a substitution problem, right? What it says is just like put, where we have f at x, just for x, just put that in, right? So if x equals 0, so f of 0 equals, replace all of our x's with whatever value we're subbing in. So negative 0 squared minus 3 times 0, that's just 0. F of 5 is equal to negative 5 squared. Very important that you keep the brackets around it. If you do not, this is going to be quite different. Do I have my pen with me? But yeah, the issue with if you don't do that, well, you're just going to get this which is not the same as this, right? Negative. Yep, so make sure you keep those brackets around. I've seen some people drop it, just something to keep in mind. Mistakes happen though, it's okay if that happens. But yeah, so we get negative 25 minus 15 is negative 40. So now we move on to g of t. We get 3 times 3 squared, once again brackets, plus 2 over 3 squared plus 4. That's just going to go to 29 over 13, right? And g of 1, well, 3 times 1 squared plus 2 over 1 squared plus 4. That's just going to be 5 over 5, which is 1. Let me find my big oil brush. Oh yeah. Okay, now we have 6. Use intervals and only intervals to describe the domain of the following functions. So this is going to have a few new things if you've never seen it before. This was messed up in the printing. This is supposed to be an entire square root. So if you see the tutorial, you're like, oh, I thought it only looks like square root of 20. No, it's square root of this entire thing. Anytime we have a square root function and we're talking about intervals of domains over the reals, what that's really saying, like suppose we have square root ax minus b. The domain of this is going to be ax minus b greater than or equal to 0. Because we want this to be 0 or positive, because if it's negative, then we're going to get into the complex numbers, the imaginary numbers. That's just not something we want to deal with right now. So in this context, we're dealing with the reals. Okay, cool. So we have f at x equals negative 3 times the square root of 20 minus 4x. So using this piece up here, we have 20 minus 4x greater than or equal to 0, which is just x less than or equal to 5, right? We're dividing by the negative here, the negative 4. Flip the sign. Once again, curly brackets mean without, and square brackets mean inclusive of, which is less than or equal. That or equal, where it's allowed to be equal, is a square bracket. If it were just less than, then it's a curly bracket. Okay, that is interval notation. The next one, suppose we have like some function g of x over ax minus b, or any number of roots on the bottom. Then the domain is such that we have ax minus b does not equal 0, because then we would have some function over 0, and well, that's just yeah, you don't want to deal with that. No. So we want to avoid the cases where we're dividing by 0, right? So if we have f at x equals this, we take the bottom, we set it, say it's does not equal 0. You can factor this. If you are not comfortable with factoring, you can just use the quadratic formula, of course. If you are able to factor, you don't have to use the quadratic formula. Some people are like, oh, am I allowed to skip steps? Yes, right? It's not even necessary. But yeah, a nice little trick that you can notice is we have negative 21 and negative 4. So we want to think about the possible combinations of multiples. Well, negative 7 times 3, that goes to negative 21. Right? And what's specifically the difference? Well, we have negative 7 plus 3, that's negative 4, so that satisfies it, right? So you want to kind of look at these two and think about like possible combinations. Sometimes it's not obvious, or it's not even realistic to solve if it's like a square root of something. A square root combination, yeah, that's a disaster. But yeah, anyways, so we solve this. We factor, we can solve each pair. That's x minus 7 does not equal 0, and x plus 3 does not equal 0. So it gives us x does not equal 7 and negative 3. Since we're only not including those values, and the original domain was over the reals, that means our complete domain is just going to be greater than negative infinity to negative 3, union negative 3 to 7, union 7 to positive infinity, right? So the next one we have a square root function and a rational function. So in this case, we're actually going to look at two pieces individually. First, we're going to look at the square root. So once again, we're just going to have x minus 2 greater than or equal to 0. That's x is greater than or equal to 2. The second one's like very similar. Well, it's just a and b again. You're just combining. X minus 5 does not equal 0, which is x does not equal 5. So now we want to look at the two domains restrictions together. So d1 union d2. Well, considering that, that's just going to give us So we have greater than or equal to 2. Does not equal 5, so not inclusive of 5. So we have 2 inclusive, 2, 5 non-inclusive, union, 5 non-inclusive, 2 positive infinity. Right. So that's it for that. 7. Ooh, this one does trip some people up. Find the functions f of g of x and g of f at x. Very important to note, this is not multiplying. I've seen some people multiply. It's not fx times gx, it's f of g of x and g of f at x. But yeah, in any case, we're given just 2 functions. We want to find basically substituting in that function into another function. So the one thing I would do that makes this very easy is write it out. Right? If you have trouble like visualizing or doing multiple steps, just write it into this. That would help you a lot. Right? So we have f of square root 2x plus 1. I'm subbing it in. So what does that mean? Well, we're going to, wherever we have this thing inside, we're going to put it where an x is. Right? So say I had like x squared plus x. And we have square root 2x plus 1 going inside. Well, that's just square root 2x plus 1 squared plus square root 2x plus 1. Right? You're going to put it where every x is. So let me just get rid of that really quick. Oil brush, yes. So yeah, we're substituting this one into that one, right? And well, what does it give us? Well, the square of a square root is just the thing without it. Those will cancel out, so we get 2x plus 1. Next we have g of f at x. So once again, we're going to sub f at x into g of x. So you can write it out if that helps you. That just means putting f at x wherever an x is. So if we have square root 2x plus 1, f at x is x squared. Well, that's just square root 2x squared plus 1. Okay. So the last piece here before I'm done, once again, it's f of g of x, just with different functions. So if f of 3x plus 2. Right, so we're going to sub 3x plus 2 into our f function. We see it's 4x plus 2 over x, so that gives us 4 times 3x plus 2 plus 2 over 3x plus 2. And you can just leave it like this. You do not have to combine, like, equate denominators, combine them. That's just not necessary. Right? This also just looks like the quotient and remainder, which is very nice, actually. That tells you a lot about the function. But the last piece is just g of f at x equals g of f at x once again. Just write it out. Substitute this into g. Since g is 3x plus 2, that just gives us 3 times 4x plus 2 over x plus 2. And we simplify, we get this. So yeah, I think that was pretty neat. There's actually a question I've never seen before. What was it? Yeah, this one. This one was actually very fun to look at. It's like a pizza slice. Ooh, that sounds really good. Hold on, bruh.